So welcome. We're going to have a lot more of these lectures from guest experts who can share interesting perspectives. Today's guest is Sebastian. I'll let him give a brief introduction, but he's going to talk to us about a very interesting topic, which is metabolic testing and VO2 max in particular. And as you'll hear from him, he has an interesting perspective that I think we can all benefit from. Sebastian, go ahead and take it away. Thank you for joining.
Thanks for having me. Just confirming you can hear me okay?
Yep.
Cool. Then I'm going to share my screen and you can quickly confirm that you can see that. It should be up here now.
It says you've started. Okay, yep, you got it.
Cool. Excellent. Okay. So as you mentioned, I'm going to give you a rundown of my background. Then we dive into the topic of performance testing, particularly on VO2 max and substrate utilization. And I'm going to start with conventional testing and some new approaches that are getting more traction, especially in the fields of sports. And hopefully there is something you guys can learn from that for your application. I assume we have, just from a housekeeping point of view, do we have a Q&A afterwards? Should we stop in between?
Let's have people put Q&A in the chat, and if we have time at the end, we can answer questions. Otherwise, if you don't mind, Sebastian, I'll send those questions over to you and you can send responses via email.
Sure. Okay, cool. Quick background story, why I'm here, why I'm doing this, and why I'm in this field. I started doing performance testing 24 years ago, initially with elite athletes and using conventional methods. And what turned out, especially in elite athletes, is its conventional methods of REM test, incremental test using lactate VO2 is or was proven to be somewhat insufficient to really mimic the performance and the performance development of those athletes. What I basically did then in 2 years at university was developing some new test methodologies which were able to, or basically looked at the aerobic and the anaerobic part of metabolism separately. And these methods at this time were so well received and so successful that I actually used those to found a human performance lab business, which grew into the biggest testing as a service business in Germany with 3 facilities and 15 employees. And it also brought me a job into professional cycling, where I stayed and coached athletes on the highest level, World Championships, Olympic Games, so on and so forth, Tour de France, for approximately a decade. Also, you guys from the US work with some, US athletes. Winning more than 10 world championships in that time with different athletes is based on this new approach on looking, so to speak, at aerobic and anaerobic metabolism differently. Then I stopped that in 2016, and in 2015 already bought some source code from a former professor of mine, sold my human performance business and started developing software, dropped out also for family reasons, dropped out of professional cycling and basically launched the software product, which is primarily focused on B2B and is currently primarily focused on sports. However, there's an increased interest from the health and wellness and longevity area, and I think that's how I ended up here in this meeting today as well. So that's kind of my background, so a little bit more sports related, but again, I hope that some of the stuff transfers to you. So with that, I'm going to focus on the 2 methodologies which are normally used. I would call them conventional testing, has been around for several decades, more than half a century, I would argue, which is used on substrate utilization and VO2 max testing. And I'm going to start with some fundamentals. Some of the stuff might be familiar, and start with substrate utilization. So substrate utilization is normally tested using a metabolic cart, as you see in this picture here. And what it tries to do is actually looking for substrate utilization, is looking at a marker called RER, respiratory exchange ratio, which is basically looking at the ratio of CO2 output, so volume over time of CO2 exhaled and oxygen uptake. So CO2 output versus oxygen uptake. If you burn 100% carbohydrates, then this ratio would be 1, because you produce as much CO2 as you use oxygen. And if you would burn only fatty acids, then this ratio would be 0.7, meaning that you have a higher VO2 uptake than the CO2 output. That's the theory. And mathematically, stochastically, it works nice. from the stoichiometry. It works nice from the chemistry. However, when we look at practical applications, there are a few issues. One thing here, real quick, I always bring up, this is a picture of a poster actually hanging here in my office, which, sorry, it's in German, looks at all the metabolic pathways. And I marked here some of the most important ones, like glycolysis, Krebs cycle, beta oxidation, what we're interested here for fat combustion, right? The idea is that training at a high fat combustion rate helps people reducing body fat, which might be related or might be of interest for health, wellness, and lifespan. If you look at that, the problem of this methodology with the RER for CO2 and O2 is that there are numerous sources in the body which produce CO2. The CO2 that you measure at the mouthpiece is not necessarily only coming from metabolism during exercise, from burning fatty acids. In contrast, when you look at where oxygen is used, there's only one place in the whole body where oxygen is used. So you could speak conceptually, there's a disconnect between what you want, like what you do see in a mouthpiece and real world application, and what it theoretically, should be happening on a molecular or cellular level. If you look a little bit further into the practical applications, there are some bigger limitations to it. And one is acute effects of diet. So I use a table here to give you an idea, because we're looking at the RER values. And again, I said RER 1.0 means theoretically 100% carbohydrate combustion, 0.7 means theoretically 100% fat combustion. And you have the table here. A number of studies, I pulled some up here, you can look at that. Here's an example. Dark filled symbols, T is trained athletes, light symbols, triangles and squares is UT, it's untrained. And we're looking at an exercise of 2 hours here. Just as an example, you can see numerous findings in the literature. And what they looked at here is the effect of fasted exercise, often done in the morning without breakfast, versus after having breakfast, not fasted. The RER, so to speak, your fat combustion that you measure with these metabolic cards, is acutely affected by the diet of the athlete or the diet of the subject, to the point where you cannot distinguish the ability to use fat as a substrate or metabolic flexibility. So all these things you would be interested in, you cannot distinguish anymore between trained and untrained people. If you look in the longitudinal or test-retest scenario, like prescribing a training program, you will not be able to see the effects, because the effects could be diminished or could be made invisible or canceled out by the actual nutrition status. We've done several of those things. I'm based here in Switzerland, so you can feed somebody cheese before a test or orange juice and chocolate. The changes in measured fat combustion using a metabolic card will be significantly different. There's also the effect of chronic nutrition. So what I brought you here is an example of a 6-day diet intervention. And one is a high fat diet, which is light bars, and one is a high carbohydrate diet. And it was basically incremental tests like you would do in a lab setting to measure substrate utilization. What you see here is that by looking at the, again, black bars for high carbohydrate diet and the white bars for high fat diet, as both the baseline substrate utilization and especially end of exercise are significantly different, not because the training status of the subject is different, not because they increase their ability to combust more fat by having more mitochondria, better capillarization, higher cardiac output whatsoever, just because of the diet they have. So this brings us to the problem that without standardizing a diet, which is obviously very different in a practical application, it's actually super, super difficult to compare findings from metabolic card data. So that's about substrate utilization, conventional methods. Then we do have conventional testing of VO2 max, which I guess most of you will be familiar with, also done with a metabolic card. How does it look like? Sorry for that. The naming here on the axis is in German, but I think we can still read it and see what it does. So what we're looking at here is a typical test protocol. It's not an incremental test. That's a a mistake often in the practical applications that people do an incremental test, meaning like 3-minute step duration, 4 or 5-minute step duration, which is too long to reach a true VO2 max. For true VO2 max testing, you would actually need a REM protocol which sees increase in load, increase in power output in an ergometer, for example, every 30 seconds, maximum 60 seconds. And based on the body weight, you normally see about 15 to 35 watts increments depending on the step size, 30 seconds or 60 seconds. You do see an almost linear increase in VO2, like you see here in the gray graph. The red one is a smoothed, the smoothed VO2. And what you do look at as a qualification criteria, if the subject really reached VO2 max, is you need to see a plateau. You need to see this leveling off effect, which you can see nicely in here. So, for example, if the test would end here, where the VO2 is still increasing, you cannot be sure if you really captured the VO2 max, because again, only the VO2 leveling off is a while, of course, in the same time, power output or load is still increasing. That is the two criteria for VO2 max. That's a primary criteria. In the literature, there's a secondary criteria, which means an RER needs to be above 1.1 or 1.15, depending on what literature you look at, which is very difficult because, again, it depends on substrate utilization of what kind of athlete you have in front of you, especially in elderly people with a low anaerobic capacity. 1.1 or 1.15 can be difficult as a secondary qualification criteria. Main qualification criteria is, again, leveling off of the VO2 max. Now, this sounds nice in theory. In practice, however, many people, especially untrained, so it's not an issue for my clients, high performance athletes, professional athletes, but especially in untrained or moderately trained people, it is very, very difficult for them to reach their VO2 max. And this effect is especially pronounced when you look at walking or running exercises. Here's a nice study. This is numbers of achiever of this VO2 max plateau using different protocol. Standard protocol like a Bruce protocol, Taylor protocol, Taylor-Mitchell protocol. You can see in the bars, some are better, some are worse, but that's not the point. The point is that no protocol guarantees that you are going to be able to find a true VO2 max in a practical application. So you have, out of 10 clients, you have approximately at least 2, if not 4, clients who don't really achieve their VO2 max. You don't have a real VO2 max measurement, which is a huge problem if you want to use this number to make any informed decision. And again, it's more pronounced in running or walking exercises than it is in cycling. So huge limitation here, and I'm not even going to talk about the issues of people need to go to exhaustion, and there might be some risk factors that you need to take into account. You don't want to bring everybody to maximum cardiac output and maximum heart rate. Okay, so that's about the conventional one. Now, that stuff is all, again, decades old. And the truth is, if you look at trends of knowledge development in biomedical sciences and computer sciences, there's a lot going on. And what I'm going to show you is how lactate, which is also getting more popular in the space, can be used for that and plays a critical role in performance testing for both VO2 max and substrate utilization. So let me start with substrate utilization. First, showing you the concept here. On the bottom, I have an article that just came out last month talking about how lactate is actually influencing and regulating fat combustion. There are several articles out. The latest one is a really great one. In general, very oversimplified without going too much into the details, what you actually put in as a substrate in the aerobic metabolism is acetyl-CoA, here in the red circle. And acetyl-CoA can be derived from beta oxidation from fat combustion, but it can also be derived from glycolysis via breaking down glucose to pyruvate and lactate. A competition, like very simplified, non-scientifically speaking, competition between those two. So if you have more acetyl-CoA coming from glycolysis, higher saturation of the pyruvate dehydrogenase, PDH, seen here also in the red cycle, then you have, simplified air quotes, the lactate pushing out acetyl-CoA from the beta oxidation, and vice versa. Vice versa means you have a subject glycogen depleted, or the effect that we just seen in the high-fat diet, low glucose availability, the fat pushes into the metabolism. And this is nicely controlled and can be calculated and simulated just looking at lactate flux or glycolytic flux. So lactate, again, a key role, one fundamental here. And then the second one that's implicitly in the previous slide, TCA mitochondria, this is the aerobic metabolism. The lactate links, it's a connection between the glycolytic anaerobic metabolism, the aerobic one. And the nice thing, which we can use in diagnostics and testing, is that the glycolytic pathway and the aerobic pathway is regulated differently. I have this one slide here, sorry for the bad quality, it's an old paper, so the knowledge has been out there for some time. The light bars is pyruvate formation, and the little bit darker bars with this stripes on there is pyruvate oxidation. So oxidative, so a marker of the aerobic metabolism. You see, I connected the upper right corner of each bar with the lines. What you can see is that the ability to combust lactate or pyruvate is going up linear. And the actual formation, so the production, the red line here, is going up exponential. And these two behaviors, these two different kinetics of glycolysis and aerobic metabolism can be used to drive very intelligent performance diagnostics, as I'm going to explain in the next two slides here. Okay, so this is how these are connected. The lactate concentration that you can easily measure in the blood, just 7 to 20 microliters of blood. Lactate concentration should be obvious, more or less, but it's implied by the previous slide also. The lactate concentration that you measure is actually the result of a certain lactate production, which is obvious, right? If the lactate concentration goes up, it has to be produced somewhere. But there's also lactate combustion in aerobic metabolism. I'm going to bring you two more papers to prove that. So that means that the concentration, I always say it's like the balance. It's like me looking on a bank account and saying, okay, what is the current balance on my bank account? And that's the result on how much influx of money I have, the lactate production, how much efflux I have, lactate combustion. Okay, and so the lactate production is absolutely proportional to the glycolytic flux, because the pyruvate that you see is actually happening in the Petri dish when you read about it in the biochemistry book. So the end result of glycolysis, that's because of the enzyme kinetic of LDH, the end product of glycolysis is approximately 95 to 98% lactate. So simplified speaking, all molecules of glucose that you want to use as a fuel during exercise become lactate. You want me to speed up? I got that.
Sebastian, I was going to say, no need to speed up. This is
Okay.
actually fantastic, and I
Okay.
don't want to cut you
Sorry.
short. So
Okay.
I just mentioned that I'm going to have my assistant join because I have
Okay.
to leave at 10:30 for another
Okay.
meeting,
No
but
problem.
you can keep going, and my assistant will be here. She will kind of keep the meeting, and anyone else who can stay, please do. And you guys can also do question and answer if you guys
Yes.
have time.
Yes. Okay.
But this is
Yeah.
fantastic. This is really
No
great. I
worries.
don't want
Yeah,
you to.
I didn't read the message during speaking. That's fine. So
No,
let
no,
me
no, no, no.
continue.
You keep going.
We are
Yeah, yeah.
70% in to give you an expectation what's more to come. Okay. And then we just keep going and you can ask any question. I'll be around. Okay. So going back, let me just recap my previous statement. What is known by now? It's different to what you might see in a textbook of biochemistry. The end product of glycolysis is always lactate because of the enzyme kinetics in vivo at 37 degrees Celsius, body temperature, and so on. All glucose you burn anywhere in the body becomes lactate. This is why we have a resting lactate concentration. And the only way how you can get rid of that lactate is via lactate combustion, which happens in the aerobic metabolism. And it's absolutely linear, as I've shown previously in the slide with the blue line, absolutely proportionally linear to the oxygen uptake. That should be obvious because as far as we know, if you want to burn anything, you need oxygen. If you want to burn more, you need more oxygen, right? This is why we have superchargers in our cars and so on and so forth. That is the whole idea. You have more oxygen, you can oxidize more. You have less oxygen, oxidize less. So the more oxygen uptake you have, the more lactate you can combust or anything else. And this is where it gets interesting because that's what we do in my background story initially, in my first slide, what we did is looking at lactate concentration separately from how much is a production, how much is a combustion. And that again, both creates, so to speak, the lactate concentration. But now it gets interesting because if you know the lactate production, and again, what I just said previously, all glucose molecules become lactate. So if you know how much lactate is produced, lactate is a C3 molecule, glucose 3 C6, so one glucose makes two lactate. If you know how much lactate you produce, you know how much glucose you combusted. So you know your carbohydrate combustion. And there's also a fixed ratio, how much lactate you can oxidize and how much VO2 you need for that. So if you know how much lactate is oxidized, you know directly, mathematically, very precisely, what is the oxygen uptake. So by looking at lactate concentration and decipher what is the actual production, what's actually oxidation, you can get all these data here. You can get the glucose utilization rate. Of course, you get something like thresholds and zone and the popular zone 2. That's normal, right, if you do a lactate test. But because you know the lactate oxidation, you can also get the oxygen uptake. This combined also gives you the fat oxidation rate, which is exactly what the literature tells us. Lactate is not only related to fat oxidation, but it actually regulates fat oxidation. This is where you can bring it full circle. By looking at lactate production, lactate oxidation, it's possible to quantify all these other metrics I'm showing here. Glucose utilization, oxygen uptake, of course, something like threshold, that's easy, that's a given, fat oxidation rate, but also then the maximum oxygen uptake of VO2 max. So let me show you some examples. This is an incremental test of only 4 steps. The steps here is 8 minutes, could be 3 minutes. It's just an example. You see the red dots here with the arrow bars is measured lactate concentration. The red line is recalculated lactate concentration, and then the blue line and the purple line is the actual combustion rate and the actual production rate. Okay, so just trying to show you what I explained before, taking the concentration and splitting it, what creates the concentration, which is production and combustion. Here's an example. This is the calculated oxygen uptake, blue line. In this case, it's a step test running on a treadmill, 5-minute steps with 30 seconds interruptions to take the lactate. So this is this normal incremental test. You see the recalculated lactate concentration with the red line, and you see a calculated VO2 only coming from lactate compared to measured VO2, which is the blue dots. Okay, so you can see it matches relatively good, I would argue. Okay, so to put this in perspective, what this means is that beside all the problems with diet affecting things, that conventionally you would need a submax test, longer step durations to get something like substrate utilization, and then you need an all-out REM protocol additionally to get a VO2 max, again, running first test running into all the problems of the diet, second test running into the problem of, am I really able to get an all-out effort? Leaving alone, do you dare to get to bring somebody to all out? I'm always bringing the example of my dad, 77 years old, a little bit overweight, high blood pressure, has a pacemaker doing 80% of the job, max heart rate. Would be super important for him to get a VO2 max, but who dares to do that? Who takes the risk to bring him to exhaustion? With the lactate-based testing, you only need one incremental test, 4 steps, and you can get it. And that means you save also an incredible amount of time. And then there's a cost for a lactate analyzer. It's just a fraction of the one for metabolic card. So that's the comparison of the old approach and what is possible with today's knowledge and computer power. And I want to give you an example on how accurate this is. This is an example for VO2 max from cycling exercises, in this case using an 8-step minute duration. So each step of an incremental test was 8 minutes. This is VO2 max calculated from lactate on the y-axis, measured VO2 max with a separate all out with a metabolic card in a lab setting on a lab grade, medical grade ergometer on the x-axis. And here's the same, it's just for running, similar like I've shown before, 5-minute step duration. And again, separate all-out, separate REM test for VO2 max. So that's that. That's some examples. And I want to finish with giving you an outlook, from what I'm currently working on, what I spend my time on beside family and sports. One thing that we are working on, which is possible only by computing power on servers, is to build in an accuracy check. We can take in the error of your measurement devices, like a metabolic cart, like an ergometer, like a lactate meter, and calculate how accurate your VO2 max is actually going to be. And the one that I'm really excited about, and we're going to publish a paper about that in the next couple of weeks, hopefully, we're currently writing the manuscript, is we built an AI which is looking at sub-maximum lactate testing. So ending the lactate test before exhaustion. What I just said for the case of my dad, nobody wants to put him into an all-out effort, but it would be nice to know his VO2 max, and basically training the AI to read or to identify, predict the VO2 max only based on sub-maximum testing, which would, again, take away the burden to take somebody to exhaustion. And on the other hand, obviously makes the test protocol even shorter. And that's, we have 26 million data sets to train on that. I'm very excited to see the outcome of that. That's the outlook. That's what we are busy with. And with that, I'm happy that I stayed within the time restrictions. Greetings from Switzerland, where we are located, and would be happy to hear more about questions that you may have right now, or comments, or any feedback that you would want to share. Thank you.
Well, thank you so much, Sebastian. As I just wrote, I have to drop now, but I did just want to formally thank you myself. This was really fantastic and at least for me, and I'm sure others in the group, insightful. I put a couple of questions in the chat that I had. So if you don't mind answering those, I will have to drop, so you'll be answering them without me there, but this will all be recorded so people can view them. There's another question that I have, which is how far off are we from being able to offer this kind of more lighter weight metabolic testing? Because I think all of us in this field recognize the importance of metabolic testing. You outlined some of the challenges of doing it in the office. Like a lot of people don't want or can't get to full effort. The equipment's very expensive and burdensome. Even some of these smaller form factor things like Panoe and Caliber, how far off are we from this sort of thing being available more broadly? And if you have any recommendations to clinicians who do want to do metabolic testing today, how you would recommend us thinking about it. So anyway, there's a lot
to unpack. Let me start with that, because the other question I've written so I can remember the other ones. What I've just shown you is done at an early adopter stage in elite sports and non-elite sports currently. If you're interested in trying that out, it's like early access, drop me an email. You got my email down here. We're currently working on the validation papers, so everything we put out is either internally or in best case peer-reviewed, science validated. If you want a number, it's always difficult in software development, but I would put a few weeks to 1 to 2 months behind it. Again, early access program is already in place, and we already have a few people doing that. That's for the one that goes to exhaustion. For the one that goes only sub-maximum, I would say by the end of the year, I've shown this validation slide here. You can see there's a little bit of fading, a little bit of a sigmoidal shape in here, and we still need some more real-world testing. So I don't want to promise the sub-maximum testing, but I am very positive that this is going to happen. I will know more about that in the next 2. But again, if you are able to go to exhaustion like you would do with a normal conventional metabolic cart / VO2 analyzer testing, that is already possible, and that has the same accuracy as a lab grade metabolic cart. So not one of these smaller form factors, aka cheaper consumer products, but a real lab grade 25-30K metabolic cart used in universities and stuff. So that's about that. How far are we out? Then going back to this question, and I hope to see more. I see already one question here. Let me first answer the ones from Anand. Is there additional value to obtaining VO2 max ARIA in addition to the lactate? I would argue no. The only, like from our users, the only use cases where people measure VO2 additionally to lactate is when they want to understand running economy. So when they're testing runners who want to complete a marathon, half marathon, 5K, 10K, whatsoever, then measuring VO2 allows you to get the metabolic and energy expenditure and compare that or plot that against running speed. You have the running economy, which is one performance indicator for running performance. You don't get this from lactate only. Or in sports like swimming or cross-country skiing, where external factors and economy, movement economy plays a big role. Yes, there is this additional benefit for the economy of movement or energy cost of movement for standard exercise testing like cycling or running or any derived from that like walking. No additional benefit, to be honest, not anymore. Second question was a lot of the outcomes related to lifespan health and benefits use VO2 max, and so many of us use that VO2 max percentiles as a benchmark. Is there any reason to believe that lactate testing wouldn't accomplish the same thing? Would we still think in terms of the same principle? Yes, we would think in the same percentiles because the lactate calculated VO2 max, as you can see in this picture, is as accurate as the VO2 max measurement. You see R square values of 9.8, 9.7. And if you do, and there's some literature, I can send this to you if you want, which compares this way of testing to the reliability of a lab grade VO2 max testing. Test to test variances show similar to maybe even lower R square values than we have here. So you normally, you can find in the literature, and that's what we use, approximately 2.4 to 2.5 milliliters VO2 max is the range. Like any differences below that you see in a test-retest scenario or comparing different athletes, you are not allowed to interpret as a difference because that is the accuracy of your metabolic card. I would see the additional benefits in that you get easier, beside lower overhead cost and lower overhead time, the additional benefits would be that you do have the zones automatically, and in VO2 testing you would need to rely on ventilatory zones, not lactate rated zones. This is more difficult, less accurate, and so on. Any way to break this down on how to make it clinically useful? Debtia, if you could, I'm not sure if I understand your question right, so if you could iterate a little bit on that while I'm answering the next questions, that would be great. Wondering on my thoughts on the core cardio coach employee, the CPEX cards are very expensive. Yes, I do have a lot of thoughts on that, and I'd be very open about that. We do have approximately 1,000 users, B2B users, coaches, human performance lab. We work with Olympic federations, Olympic team, professional team. We work with hospitals. We have a vast variety of users with a vast variety of machines. And we do have this quality check when you upload the data. Our algorithms are able to identify if some data doesn't make sense. So for example, if your VO2 that you measured does not fit to the running speed or power output. We also have feedback from the users. Unfortunately, it's not very good. We have a lot of unhappy users about it. The data that we get is often not good. Retest reliability is not good. It's not a true breast-by-breast device. There's a caliber out there which looks good on paper, looks good in an isolated lab setting. Real world application is still difficult. Not saying they cannot get there, but I would argue it's not quite there yet. There's a VO2 master, which I have a long history with, which can work pretty good, but in the recent 1 or 2 years, we have more and more users complaining about the data. So yes, it is difficult. If you don't want to go to a full-fledged metabolic card for 5 figures, it is really difficult. I was asking if you go for CPEX, VO2 max LTs, a local university, can I use the insight to calculate my own output? Yes, you can put VO2 data in our software. However, you can also run it on lactate only, which is what most people are doing. Theoretically, you can. Core cardio coach, most people have pretty good experience with that. If money doesn't play any role here, it would maybe not be the one that I recommend, but in many cases it works better than the really small form factors one currently. If I may go into a small rabbit hole here, one of the main problems of VO2 analyzers is, especially if you look at the VO2, leave alone the VCO2, the VO2 analyzers share, almost all the devices share the same sensor to measure oxygen concentration, which is a chemical cell. The problem with that is that first, it doesn't like any humidity. It doesn't like any water. So you need to dry the air, which is what normally a metabolic cast has the tubes for. So it's a big challenge for something like a VO2 master is to dry the air without the long tube. The second problem is that the calculation of the oxygen concentration, which is part of the VO2 equation, so it's calculated VO2 actually, right? It's calculated VO2 in these machines. You just don't see the calculation. The calculation depends on the temperature and humidity. Changes by approximately 10% if the temperature of the sensor changes approximately 0.1 Celsius. So it's super sensitive to that. This is why you need to warm these machines, and this is why they have a thermometer in there that measures it, and VO2 Master can give you a report of temperature shocks and so on and so forth. So basically what I'm trying to tell you, and that's often overlooked, the reason why those machines are so expensive, 5 figures, is not because they are rock solid accurate. It's just because it's a very complicated piece of equipment. And because it's complicated, it can be easily affected by temperature and humidity. So recommendation would be go for a full metabolic card if you have to, or what we are working on and what we achieved for the normal incremental test to exhaustion. You can get the same from lactate only. And this is at least more robust. Accuracy is as good, and you don't have to deal with all the problems with temperature and so on. That's my take on it. And if you want to chat more about that, just reach out. You have my email here if you want early access to these things with the lactate step test protocol, or this submax one where you don't have to go to exhaustion, this AI-based one when it's done. Reach out, and I'm happy to give you early access as part of the program. With that, I don't see any more questions coming in. Yeah, send me questions for sure. Go ahead. You got my email. It types the email here so you can copy paste it as well. That's a little bit more convenient. Okay, go ahead and do that. I will stay 30 more seconds if you have more questions in case somebody's typing. I cannot see if someone is typing, so I give you a little bit more chance. If not, it was a pleasure to meet you. And if there's more questions or something, please reach out. And I guess you will get the recording and the AI transcript. Thanks a lot. Have a great evening, afternoon, day, depending on where you are. Maybe be in touch. Thank you.